Yes, we'll have Alfonso. Alfonso is a software engineer at Weaveworks, and he was previously at Spotify, and he'll be telling us about how to high-performance Linux monitoring with eBPF. Okay, Alfonso? Welcome.
Hi. As I was very kindly introduced, I'm Alfonso Acosta. I'm a software engineer at Weaveworks. And I'm going to be talking about monitoring with a technology called eBPF. But before I start, I would like to ask a few questions so that I can address you guys. So who has used TCP dump here? OK, almost everyone. Who knows what BPF is? 3 people. OK, this is going to be interesting then. Who knows how to code in C? How about Python? OK, how about Go? OK, great. And finally, who heard about Weaveworks before coming here today? Great. So in case you didn't know about Weaveworks, we are a small startup based in, well, the headquarters are in London. We have offices in Berlin and San Francisco. And our ultimate goal is to simplify the development, management, and administration of microservice-oriented applications, which are typically containerized. Among other products, like WaveNet, which you might have heard about, we have a product called WaveScope. And I'm introducing WaveScope not because I want to market it here, but because it's relevant. We are introducing eBPF in WaveScope. But what's WaveScope? WaveScope lets you visualize, monitor, and control your microservice-oriented applications. What we see here is actually our cloud service called WaveCloud, monitored in scope. Each of these nodes represents an entity in your application. In this case, they are Kubernetes services. Edges represent connections between them. And the clouds represent external entities, like a cloud service or a connection to a server on the internet. So what are we going to be talking about today? We're going to be talking about BPF. We're going to be talking about eBPF, which is an extension to it. It lets you do dynamic tracing in Linux. We're going to be seeing as an example how you can get HTTP metrics on a service without instrumenting it. And we're also going to see how we're going to use eBPF in WaveScope to do accurate and high-performance connection tracking. Can anybody tell me what this does? I'm not going to continue until somebody tells me. So we can spend here all day.
HTTP traffic in theory.
OK. So it captures HTTP traffic. It will show you all connections, the traffic of all TCP connections, which have destination port 80, which is a port typically used by HTTP. And can anybody tell me how this works under the hood? Any ideas, suggestions? Again, I'm not going to continue until at least I get a suggestion. So, somebody? It gets traffic, but how is the traffic obtained? Any ideas?
Network interface.
From the network interface, sure. But do you think, so the packets are going to be copied from the kernel to TCP dump somehow, right? Who thinks that all the packets are going to be copied to TCP dump and then TCP dump filters it? Raise your hand. OK, 1 people. 3 persons. So, and who thinks that only some packets are going to be copied to userspace? And 4 people, 5 people. And the rest don't care. OK. Actually, it uses BPF. So BPF stands for Berkeley Packet Filter. And it's a technology used, it was introduced in 1992 in BSD. That's why it has a Berkeley. And it's used to filter packets. So the idea is you execute a program, a small program on every packet received on certain interface on all of them, depending on what you choose. And then that program decides whether that packet is accepted or not. That program is encoded and executed by a virtual machine within the kernel. So you define certain instructions which analyze the packet. The memory in which that program operates is the packet you're filtering. And then it returns true or false. And if it's based on that value, it either goes through the filter or the packet continues its normal path. And TCP dump uses that to do precisely that. The original paper is quite interesting, actually. So here's what TCP dump does. TCP dump creates a filter, which is TCP on destination port 80. It provides that filter to a library called eBPF, which works on Unix and also in Windows, but in Windows it doesn't use BPF. eBPF compiles that to BPF bytecode, injects it in the kernel, and then the kernel does the filtering based on that BPF program and returns the packets to TCP dump. Let's see it at work.
Just one quick question.
Yeah.
Is that OpenBSD's and FreeBSD's PF? Is that the same thing?
I think it's available on both. The question was whether it's available in FreeBSD and OpenBSD.
Is it the same piece of?
They originally come from the same software distribution, so I guess it will be available in both. I actually only have tested it in OS 10, which also comes from BSD. And I'll be showing that in a bit. So first, let me show you that at work. I have TCP dump working here. And then I do a connection to Google, and then you get the packets. OK? And this is instruction set. Just to show you, I'm not going to get deeply into it, but just to show you it's a limited but still a machine instruction set. It has some logic and arithmetic operations. You can load and store in memory. And it has different indirections you can use. You can either use absolute addresses on the packet. You can use a memory pointer, so on and so forth. In fact, let me show you. I downloaded a project called BFD compiler, which takes an expression from a pickup expression, and it generates the resulting bytecode. So you do BPF comp, output. It will output the codification of the instructions, and then you write the expression, which was TCP and destination port 80. And it vomits this. You don't need to understand what it does exactly, but just so you can see the mechanics of it. OK? And in different operating systems, it has a different API. So in OS 10, you open a special device, which is that BPF 0, 1, 2, 3, etc. It runs an IOCTL on that file descriptor, which provides, well, this type of IOCTL and the bytecode. Well, this is actually to set the interface on which you want to sniff. Sorry. So you will provide the Ethernet device or any other device you want to apply filters to. And then IOCTL BIOS set F stands for set filter, lets you load the BPF filter. From then on, when you read on the file descriptor you open, you should be able to get raw packets. And in Linux, it uses a special type of socket instead of using a device. It's sock raw. When you bind the socket, you provide the interface through the address structure, and then you have a set sock option to attach the filter, and that's it. When you read from the socket, you'll get the raw information. Now, maybe this is a bit too low level, but I created a couple of programs to demonstrate this. Let's go for the Linux one first. Actually, I forked this from somebody who already created a demonstration program, and I modified it to do what we wanted. So yeah, what happens here is here's a load instruction of H, which is a big word, on the offset 12. If you check the Ethernet frames and the structure they have, on offset 20, there's the type of protocol being transported. So what we do then is compare the value of the protocol with Ethernet IP. If that's equal, that means we want to accept that packet. If it's not, then we jump to reject, which is in an offset of 5. 1, 2, 3, 4, 5. And we do exactly the same for the other checks we want to do. So in order to obtain the type of protocol within the IP packet, we use offset 23, which is the 14 bytes of the Ethernet header plus 9 bytes in the IP header, and we compare it against the type we want to check. Again, if it matches, then we continue checking, and if not, we return reject. And we do exactly the same for the port. And we actually cut a corner because we assume that there are no options on the TCP on the IP header, but I mean, more or less you get the idea. Then this gets, let's see where this is. We attach the filter like this, and then we run it. So let's run this, this code. Okay, I downloaded it. Okay, I compiled it. And now I need to figure out the interface name. Let me check. I'm pretty sure it's this one. This is a Linux virtual machine, by the way. And I'll probably need to do it with sudo. So this is running. And when I do curl, nothing happens. But let's see, maybe it's 9. Okay. Okay, well, I tested it at home and it worked. Imagine some packets would show up there. The idea was to show the mechanics of it. I think I may not be using the last version of the code because the link is broken. Okay, never mind. I'm probably not using the right interface or something like that. Okay, now let's look at the OS 10 version. This one's a little bit different because it uses, instead of using absolute addresses, it uses a pointer register to increment what you're pointing to in the packet and makes management of the program easier because then you don't need to manually compute the offsets. But it does something pretty similar. It checks that it's TCP, it checks that it's port 80, and in this case I think it also checks that it's either a destination port 80 or a source port 80. Let's try to run this one, and hopefully this time it will work. This I'm running in the Mac, by the way. Yeah, and actually, I don't think I need to run it as a super user. Let's see. Okay. Yeah. So in this case, we print the MAC addresses of the packets. Okay. Any questions so far? So that was BPF, which again is available both on BSD operating systems like OpenBSD, OS 10, and I think FreeBSD as well, and also in Linux. Now, BPF was extended to something called eBPF, extended BPF, and it only works on Linux, but it's in mainline. And by now, most, if not all, software distributions will come with eBPF out of the box, which is fantastic, because it means you don't need to load any special kernel modules or anything like that in order to use it. The same applies to BPF as well, but it's not as powerful. Since BPF was extended, the original BPF is called now Classic BPF or cBPF. It's also a technology which uses a virtual machine in kernel and executes programs described through a bytecode representation, which makes them architecture independent, by the way. But the instruction set of eBPF is much richer. It has 64-bit registers, actually 10 64-bit registers, which makes it easy to map with the host architecture on the fly. So you can do a map of registers and translate to native instructions very easily. It also comes with an LLVM backend so that you can code your eBPF programs in C and translate them to eBPF, which makes it much easier than what we saw on the screen, coding in assembly or actually in binary pretty much. Who's familiar with LLVM here? Raise your hands. LLVM is a compiler technology which allows you to easily create compiler backends. Actually, Clang uses LLVM, and it's what the OS 10 compiler uses. Although I was using GCC. And the most important new feature from eBPF, it's not that the virtual machine is more powerful and the instructions are more powerful, but that it allows you to do dynamic tracing. What's dynamic tracing? Anybody can tell me? No?
You can run while you're running a program. You can so to speak, monitor what's happening inside with pre-existent triggers.
Okay. So it lets you inspect a running program on the fly without modifying it in any way. and it allows you to do that in the kernel. And it supplies something called maps and events to communicate with your eBPF program. And it's actually safe. There's an in-kernel verifier which will guarantee, well, let me refine that. It won't crash. It's safe. It can be safe or not safe depending on how you use it, right? If an unprivileged user manages to inject an eBPF program in your kernel and gathers information which shouldn't be there, then maybe it's not safe. But it's safe in the sense that it won't crash your kernel, and we'll see why. But before we jump even deeply on eBPF, let me describe a feature from the Linux kernel for you. This was introduced in 2.6 or even earlier, so it's been in mainline for a long time. And it allows you to do dynamic tracing. So let's assume this is a kernel space memory, and you have a bunch of instructions. And you want to see what's happening when the kernel executes instruction 3. So what Kprobes do, and this is the optimized version, it's similar to what a debugger does when you set a breakpoint, right? You replace certain instruction, redirect the control flow to something you can manage. What GDB does in normal debuggers is they insert a trap instruction which sets an interruption. But in this case, to make it even more optimal, you insert a jump instruction, save the context of what the kernel was doing, execute a Kprobe, your Kprobe, the code you've injected, restore the context, and jump. And in fact, this is wrong. I'm going to correct this on the fly. Because you cannot simply remove instruction 3 and be happy with it. Okay. Now it's correct. Okay. But Kprobes before eBPF were super powerful, but had some limitations. They were typically injected in kernel modules. Kernel modules are difficult to code. You need to be super careful. You can crash stuff, so they're unsafe. The code will be architecture dependent, right? You'll code it in C, but then you compile it. You need to compile it to the specific architecture. Then you need to inject it, and so on. And the code will be fragile. When you specify where you place the Kprobe, you need to somehow specify the instruction where you want that jump to happen. That typically is done through a symbol and an offset in that symbol. For instance, if you want to inspect what happens in certain system call, you specify the symbol of the system call and offset, well, it depends, wherever you want. 0 maybe if you want to do it before the parameters are obtained from the stack. And it's also kernel version dependent. The symbols, if you want to inspect something which is not stable in the kernel, which will be pretty much anything, you'll have a hard time making it work in different kernel versions. There's a workaround or an alternative to this, which is insert the Kprobe in something called trace points, which are stable. There are points in the kernel where you inspect what's happening, but they're static and predefined. So if you stick to trace points, then using Kprobes is going to be pretty limited. Okay? Any questions until now? Okay. So with eBPF, we can define our bytecode program, but instead of being used to filter packets, we can inject a Kprobe in the kernel defined by the bytecode. And it's safe. It's limited in size, so the kernel won't accept programs bigger than 4K, 4 kilobytes. And there's an kernel validator which makes sure that your program is safe before executing it. So it does things like make sure there are no loops, validates the arguments passed to functions, and so on. This will make your eBPF code fairly limited. If you don't have loops, then maybe I shouldn't dare to say this, but I think it wouldn't even be Turing complete. But you can do a lot of stuff with this. It's architecture independent because the eBPF code is. The bytecode defines a virtual machine. But it's still fragile because even if it's eBPF, even if it won't crash a kernel, you still need to inject it somewhere. And that somewhere may change between kernel versions. At Weaveworks, we've managed to overcome that and through offset guessing in data structures. But that starts to turn things into almost like a virus, right? Which goes through memory and tries to figure out where it is and what the offsets are. And eBPF supplies mechanisms so that user space can communicate with the eBPF code within the kernel. It supplies something called maps, which is a map, a key value store. It can be a histogram, which is very useful to store metrics on what your system is doing. It can be simply an array. And your user space process can communicate with your eBPF program through that map. It's very useful because it supplies buffering for operations. So imagine you want to do something in the kernel in packets, for instance. And let's say you want to count the amount of TCP packets going to your kernel. There are counters for that, but let's assume you wanted to do that through eBPF. If you pass every single packet to user space, that would be super expensive. But if you accumulate that counter in a map and gather it temporarily from user space, that would be cheap. You can select the frequency in which you do that polling, and it would be very efficient. Now, here's another mechanism which you can use within your eBPF probe, and it's called perf events. Perf events have predate eBPF, have existed in the kernel for a few years now. But you can use them to send events from your probe to user space. In the same fashion, imagine you want to get, I don't know, whenever a specific port is accessed, you want to know it from user land. If you use a map for that, then you would need to poll regularly. Has this port been accessed? Has this port been accessed? Has this port been accessed? And with an event, you can send asynchronously whether something happened. But how do you do this? How do you work with eBPF at the low level? I'm going to be talking about how you do it at the high level. There's a system call in Linux called BPF, which allows you to load the program, which can be, let me highlight this because it's important. The same infrastructure can be used for injecting Kprobes, but you can still use it to do packet filtering, like we saw on the TCP dump example. In fact, the old BPF infrastructure internally converts the BPF bytecode into eBPF and uses the new eBPF engine to do that. You can use the same BPF system call to manipulate maps. You can create a map. You can get elements from the map, store elements in the map, so on and so forth. And it's a system call with all its implications. Context changes, so on and so forth, so you shouldn't be doing it super often. Once in a while is completely fine. And you can also attach the perf events. You use perf event open, which again, it existed before eBPF, but what's new is a new IOCTL call, which allows you to connect the file descriptor of a BPF program with the file descriptor of a perf event. Now, working with assembly is a pain in the ass, particularly if the program gets more and more complicated. So I mentioned that there's an LLVM backend which allows you to code your probes in C and compile them to eBPF. But to make it even simpler, there's a front end written in Python called BCC, BPF Compiler Collection. You write your program in C and you use Python to compile it on the fly, inject it in the kernel, communicate with the maps, etc. And I'm going to be demonstrating BCC with scope. So what I'm going to be showing is an HTTP server, Nginx, and some client making HTTP requests to it. And without instrumenting Nginx, I'm going to be able to get statistics on those HTTP requests. I'm going to be able to get the requests per second, the 200s, and the 404s in this case. Okay, this is done through scope plugin, which is here. So I have scope running locally, which doesn't show much, just the weep scope container. It's pretty sad. But I'm gonna run an Nginx container, which is gonna be listening on port 80. Actually, I'm gonna run it in the foreground. So that you can see the request flowing. Okay. There's my Okay, TMUX is not liking me too much today. But okay, so the container is running, and we can see it appearing in scope, but nothing's happening yet. And then I'm gonna load the plugin. Just make it. So what has happened here is that it has loaded the eBPF code with BCC. It has compiled it. It has injected it in the kernel. And now it's sending metrics about HTTP to scope. Now, no metrics will be available because nothing is happening. So what I'm going to do is I'm going to use a client which is this big enough? Can you see this? Okay. No? Okay, let me make this larger. Is it better now? Is it better? Okay, so it simply connects to port 8080 regularly, which is where Nginx is listening. And we're going to do that. Okay. And now, well, sorry. This is the Nginx tab, and we're seeing requests flowing. If we go to scope, we'll see all the processes connecting through the Docker proxy to Nginx. It shows the dead processes as well. And we see the plugins, the HTTP plugin container and Nginx. If we click on the process, we see, voila, we see the HTTP requests. And we haven't modified Nginx in any way. It's just plain Nginx. Now, without getting too deeply into it, let's look at the plugin code. So this plugin has a C file with the eBPF code and a Python script to govern it. The C code is maybe a bit complicated, but let's describe the basics. So it defines kprobe skv copy datagram iter. What this does implicitly by its name, the name of the symbol, is it injects a kprobe with the code in the body of the function in a kernel function called skv copy datagram iter, which is what copies the information of datagrams from kernel space to data, to userland, sorry. And what we do is we inspect the data and try to figure out whether that data is an HTTP request. So remember, we cannot use loops. That's important. So we verify that it's TCP, and if not, we don't do anything. We verify that it has a minimum length to be HTTP so that we can access the data. And again, if we try to access data because we didn't handle our pointers correctly, the eBPF program would stop running, but nothing will crash. That's important. And here we obtain the data, and we do crazy things like this to figure out if it's an HTTP request. And we do this because we cannot use loops, right? So we check if the first letter is a D, then we check the second letter, so on and so forth. And it's a delete. If it's not a delete, it could be a get, it could be a head, and so on. The eBPF guys are going to include some library functions you can invoke, which will be safe. So you'll be able to do things such as string comparison safely. But maybe it's even merged already. But at the point we wrote this, that didn't exist. So we did it this way. And finally, yeah, let me show you that as well. We govern this through Python, which is BCC. So we import BCC and friends. And what do we do here? Actually, I'm reading this code for the first time in a long time. So you get the table from the kernel and iterate through it, compute the request rate. I store it locally and forward it to scope. And somewhere here, we'll inject the code. Let's see if there's something called load. OK, no. But anyways, this uses BCC in order to compile the eBPF program, which is encoded in C, loaded in the kernel, and executed and grab the statistics from a map, because you don't want to get every single packet from the kernel in order to examine it. Now, as you've seen in scope, we need to do connection tracking in order to show edges between nodes. That is not a simple task in Linux if you stick to what the operating system provides. So are you familiar with netstat? Please raise your hands if you are. So netstat gives you information on what connections are happening in the operating system. And what netstat does internally is it checks information from the prog file system. It checks the file descriptors to see if they're sockets and they're associated to a PID, and checks the connections, which are actually in prog/net/TCP, puts that information together and presents it to you. And to get a snapshot of what's happening in a specific moment, that is fine, although racy, because you're not reading this to you guys atomically, and things can change in between. So it's racy by nature. It's even worse if you want to catch every single connection happening, because if you do polling, every time you poll will give you a different picture, but you won't be able to track the connections in between those pictures. And you can do polling very fast, but still you have no guarantees of catching it. Plus, it will consume a lot of CPU. Even worse, you don't get NAT information. You get the final addresses, but you don't get information about how addresses are being translated, which is essential in order to present what's happening in scope. As an alternative, we started using contract. Contract allows you to track connections, and it gives you NAT information. It's event-driven, so you don't need to poll, and it was much nicer, but it doesn't give you PIDs. And without PIDs, you cannot associate it to a specific process. We started doing things such as, okay, but let's assume that the IP of a container is unique. So if that IP is unique, and we have a connection coming from that IP, it surely comes from that IP, right? But what if you have multiple processes running in the same networking namespace? You start to get more and more and more problems. What if a container is running in the host connection namespace? Then you cannot univocally determine whether that IP belongs to a container or another. So it starts getting complicated. So we started working with a company in Berlin called Kprobes, and working with them, we decided to port the connection tracker to eBPF. We started by using BCC, and that worked well, but the problem with that is that it uses Python, and scope, which is open source, by the way, is coded in Go, and we didn't want to deal with the Python runtime in the scope container, Docker container. And it has runtime dependencies. BCC is very convenient, but it needs you to have LLVM in the system when you run it, which was making our container grow from 50 megs to something like 150 megs, which sounds like not a big deal, but you want to keep your containers lean. And it also depends on the kernel headers, and this was the worst dependency of them all. In order to run scope, we want to make it simple, so we don't want system admins to, okay, in order to run eBPF, you need to make sure you install the kernel headers, and you need to mount the kernel headers in the container. Because with containers, as you know, the one thing which you cannot pack and change in the container is the kernel itself. So you would need the exact headers you were running in the kernel. And it was still fragile, so we need to inspect the socket data structures in order to obtain that kind of information. And although it doesn't change too much, that data structure can change from kernel to kernel. The offset of where things are can change. The socket data structure is full of if devs, which, even worse, doesn't only depend on the kernel version, but the specific configuration of that kernel when it was compiled. So what did we do to solve that? In order to stop using Python, we created a binding of BCC in Go. So no runtime dependencies on Python. And also, it would allow you to load eBPF bytecode instead of requiring to compile the C code in the file. So no header dependencies anymore. And but how about the fragility of the code? So what we do is a crazy thing, which is when our eBPF code starts, from userland we create TCP connections, which we know should get some values on the kernel data structure. And then we guess the offsets of the data structures by inspecting those connections we can control. That makes it less fragile and kernel version independent. This is going to be released in the upcoming release of Scope, which is Scope 1.3. And if we incorporate GoBPF and the tracer to this graphic, so GoBPF doesn't have the same features as BCC, but it's a little bit easier to use when it comes to runtime, not development, because you don't depend necessarily on the kernel headers anymore. And then we have the TCP tracker, which is super easy to use, and it's independent from the kernel version and the runtime and so on. But it only provides tracking on TCP connections. It doesn't provide the dynamic tracing support, general dynamic tracing support of eBPF. Now, to finish my talk, let me show you a demo of connection tracking in Scope. And for that, I'm going to show you our cloud solution, cloud.weave.works. So when you log in, you're offered different instances which you can look at. And I've enabled the scope probes with eBPF in our development environment. So I click on Explore. And this is a bit meta, because what we're going to see is Weave Cloud monitored in Weave Cloud, the development environment. So what we see here is the live connections of our development environment tracked with BPF. In this particular case, we're seeing the Kubernetes services talking to each other. But if we want to go bananas, we can show the container or the processes view. And we're going to see this herbal here. We're using Prometheus for monitoring. And Prometheus pulls data from pretty much everybody. So that's what you're seeing, that herbal around it. All these connections are being tracked by eBPF. By the way, we also have, if you don't want to see those herbals, we also have a table view, which allows you to monitor your cluster with a top-like tool you may be familiar with. Finally, if you want to, I'll be sharing these slides. Actually, I already did in my Twitter account. If you want to learn more about BPF, eBPF, and how Scope uses this, go through these references, which is what I read when I was developing this. So you will find it useful. And that's me. Do you have any questions?
Thank you for this interesting talk. Have you benchmarked the overhead in production of running this kind of monitoring?
The overhead of eBPF is fairly low, and in fact, the probes will run will consume less CPU using eBPF. When I say probes, I'm talking about scope probes. Before, what we were doing is we were going through prog all the time, which caused a lot of read system calls, and it wasn't accurate. So in terms of performance, it's better. Maybe not dramatically better, but better. But we're doing it mostly for accuracy reasons, not for performance reasons.
Okay. Do you have any kind of figure as to what the overhead would be? I mean, from the same process running without probing and...
But are you talking about the kernel overhead, or are you talking about the user land overhead?
Well, both.
The user land overhead will be fairly low, right? Because the eBPF code is running in kernel space, and you're accessing data. You need to be careful about performance, of course. You don't want to pull maps every 5 milliseconds. But the eBPF work has been implemented by really smart people who have been using tracing for many years, so it's really high performance. I don't have specific benchmarks for you if that's what you're asking for, but I'm sure you'll be able to find them in literature.
Okay. And I have a further question, which is, I will try not to sound confrontational.
That's okay. I like confrontation.
Why has it taken so long for what is essentially a development of dtrace, which has been rock solid in Solaris for 10, 12 years?
That's probably a question for Brendan Gregg, who is the original
which I
player.
haven't seen in the. I was a bit surprised not to see him in the list of readings, or maybe I have not.
Not him specifically, but perf was coded by him, and he's behind BCC, so you'll see him in all the GitHub issues. Frankly, I don't know. Actually, there was a port of dtrace. For those who don't know it, dtrace is a dynamic tracing system originally included in Solaris, and which also works on OS X. I didn't mention it because we're Linux-centered, and I wanted to talk about eBPF specifically. But with eBPF, you can provide the same kind of functionality, but in a much harder way until this point. If BCC and other tools improve, then it will become easier. But if you want to experiment with dtrace, you can do it out of the box, I believe, on your Mac. But again, that's a question for Brendan. Maybe here they didn't want to make the effort. Maybe, I don't know. There was an effort I followed for a few years, which was porting dtrace to Linux. But it never made it to mainline, and I think it was pretty unstable. I played with it many years ago. I would say even 10 years ago, could be. Yeah. Yeah, there was an initial port. I don't know. I think that development stalled.
So the way on Linux would be more like tools like BCC rather than high-level languages like dtrace?
I would love to use dtrace, but you simply can't. There are other solutions like SystemTap and Friends, but they require installing a kernel module. And frankly, I don't think you want to do that if you have an alternative.
Okay. Thank you.
Any other questions?
This is going to be very similar to the last question. What is the kind of kernel overhead difference between your kind of Go connection tracking and just the contract module? Do you know?
So that depends on what you consider kernel overhead. Would you consider the system calls in general kernel overhead?
Yes.
Then it's lower because we don't do polling anymore. That means we only probe specific calls which are related to creating a connection or stopping a connection. When polling proc, you're doing a hell lot of read calls and directory listing calls in order to obtain the processes. So I cannot give you specific numbers, but the overhead is definitely lower. I would challenge anybody to show me otherwise.
I mean specifically the contract kernel module. I have some stories about that. Like I wouldn't enable contract on any sort of system where I have a lot of short-lived connections. Because it will can and will take down the box if you because it's just far too much overhead, and that's supposed to be kind of
low
it's not
overhead.
polling,
Yeah, that's work we still need to do. We haven't. Again, this hasn't been released yet. It's not going to be enabled by default, but I don't have an answer for you, unfortunately.
Cool. No problem. Thanks.
Okay.
Any other question?
As far as I can understand, this is not released yet. Before
It's merged in master in scope, so you can try.
Before doing that, how you were inspecting the connections, the edges between the nodes?
As I described here.
Maybe I missed that. Okay.
Like this. We still use that as a fallback. So if for some reason, well, first, eBPF will be released in the next version of scope, but it won't be enabled by default. We want to test it thoroughly for reasons like the question of performance, but you will be able to use it. And unless you enable it explicitly, this is how connections will be tracked, which has been a big headache. It's really hurry to track the connections if you don't have a good API with the kernel.
Yeah, right. Okay, thanks.
Last question, David?
Hey, so sorry, but at some point you said that lib pickup implements the regular network filters you see in eBPF now?
It translates
your
the pcap
filter
expressions to BPF.
to BPF.
To BPF, classic BPF.
Classic BPF, and that definitely has way more overhead than eBPF traps, or
No,
not?
because internally the kernel, well, the kernel translates BPF to eBPF, which only needs to happen once. And then the JIT, it has a just-in-time compiler, which has a, for most architectures, it has a really easy mapping from eBPF bytecode to native code.
And then how hard, I mean, wouldn't it have been way easier just to go to lib pickup way if you are basically getting the same connection cost?
The problem with that is that that's connection filtering. You cannot get the PIDs of processes with that. You can see what's happening from what IP to what IP, but you cannot attribute it to a specific process. And without a specific process, you cannot draw a graph. Okay. Or you can in some cases, but in some others not, and you want to kill yourself debugging it.
But
you know.
Just to get the idea that basically the overhead would be similar if what you need would be doing lib pickup or something like that. It's definitely way easier.
It would be much higher, in fact, because you want to track all connections. So you would be pretty much sniffing on every single packet in the system. So, no. I don't know.
Yeah, basically because lib
you
pickup wouldn't allow you to accumulate in the kernel, so you would need to be swapping for each one. Yeah.
You don't want the payloads. You want when a connection happens and it stops happening. Yeah.
Alfonso, thank you.
Thanks.